To MME 305. Um, the the major the major aspects of this course are the first is that we want to identify and be aware of common instruments that are used to measure and record experimental variables within mechanical engineering, um, common applications of mechanical engineering. Our second goal is to be able to design an experiment, like a test plan, to obtain basically enough statistical information to help make a decision. Right? And our last goal is to properly utilize a measurement system to be able to interpret data and be confident in the experimental results. So basically being able to assess the uncertainty of the measurement and whether or not we can trust the data that we did collect, and it can be used effectively to make good decisions. So a measurement system typically always starts with a process. Okay? So the process is basically what we are trying to measure. Okay, so it could be let's just take temperature for example. So we want to measure the temperature of the air in the room. In order for us to do that, we need to select an appropriate sensor that can measure that temperature. Okay, so that sensor might output a very small change in, let's say, electrical resistance. Okay, um, and that electrical resistance, um, all right, um, can be converted. I guess the change in temperature is converted to electrical resistance. So, and then that electrical resistance might want to be measured or amplified using a signal conditioner. Okay, so some examples of signal conditioners would be like an amplifier if we want to increase the variable, the strength of our signal, or um, uh, a um, or a filter if we want to eliminate some electrical noise. Right, that signal then goes into our data acquisition or our multimeter, something like that would basically tell us what the value of that resistance of the sensor is. All right, so that might give us an output that could go to a computer or maybe just a screen on the multimeter itself, or or sometimes it can go to a controller, and that controller might be used in order to control the process. So, for example, a common controller would be like a thermostat in the house. It would measure the temperature of the room and it would adjust and turn a furnace on and off in order to monitor that, to keep that temperature within a desired range. So, so what this actually physically looks like is for a load cell, for example, right? The goal of a load cell is we want to measure the force being applied. Okay? All right, so that force, all right, being applied is in the load cell is going to get converted to a voltage. Okay? That's the basic principle of the load cell. So the voltage is proportional to the force being applied. Right? That voltage, however, is pretty small, right? And it can be difficult for us to read directly. So what we're going to do is we're going to feed that voltage into our amplifier, right? And basically, the amplifier basically says that the output voltage is proportional to the input voltage times a gain. Okay? All right. Now that our signal is much larger, the output voltage we can read either using an oscilloscope or a multimeter or some other type of data acquisition device. And a lot of times these data acquisition devices get read and fed into a computer, right, where we can do some data analysis, some visualization, and we can use that data often to calibrate our instruments. Okay, so that's a common example of what we're typically doing in this class. Most of the weeks in the labs we'll identify a different type of sensor transducer that we're going to use. We'll use appropriate signal conditioning as necessary before we read that signal using a data acquisition device. Okay, that's the major flow of the course. So you might be asking, where are these types of measurement systems used? All right, and what are the purpose of them? So most measurement systems can be broken down into three common functions. The first one is probably the simplest. It's just if you want to measure a physical quantity. So um, oftentimes, if you go to the grocery store, for example, you get charged when you check out for fruits and vegetables by the mass of them, right? So they basically have a formula where they'd say you pay 50 cents per pound of bananas. All right, so when you go to check out, you weigh your bananas, and then it basically calculates how much you owe the store. All right, so that's an example of regulated physical measurement. Monitoring functions is also common. All right, so for example, when you go outside, you might want to know what temperature it is, all right, or if it's going to rain. So you're going to check the weather forecast, all right. And a lot of times the weather forecast will tell you what the temperature is, and it might tell you what the pressure is going to be. So if you have a pressure drop, you're going to most likely have rain. All right, so that's an example of a human using data to make a decision. All right, and then the last case is like an automatic feedback control system. So an example would be like your thermostat in your house or cruise control in your car. And the idea here is that you want to maintain a desired set point or a profile for your measurement, and you're going to adjust the process in order to maintain that desired value. And as sensors have been getting cheaper and their electronics in general have become a lot more cheap, they have been integrated into a much, much larger amount of cars. So, for example, a typical modern automobile has 60 to 100 sensors within it, and all those sensing outputs get fed into an ECU or an electronic control unit, which regulates the car's function. So all measurements have to include some type of dimension within them, okay? So dimensions are defined for basically the 6 base dimensions, where all other dimensions kind of come from. These 6 base dimensions are defined here. So we have a SI unit and a base unit and some common conversions between the two. And on this table, we have derived units. So these are dimensions where basically they're made out of they're made or determined from the base dimensions. All right, here. Okay, so these are common ones that we run into within the class. So in order for measurements to be able to be properly determined, we need to basically have a standard way of calibrating or basically verifying how accurate our measurements are. So one way to do this, and a common way to do this, is called a hierarchy of standards. And the idea here is that there's a primary standard that's regulated by a government or international agency, right? That's maintained as the absolute standard, right? We can then use that primary standard to create very accurate instruments that are reference standards. And then we can use reference standards to then create or transfer standards and local standards, and eventually working standards, which is what most people will use for their instrumentation. But basically, as we go down this hierarchy, we typically are losing accuracy. But we are able to kind of, if we want to verify if our working standard is working properly, we can go up to our local standard. And then if we want to determine what our local standard is working properly, we can use the transfer standard in order to verify its accuracy. And kind of just keep going back up to make sure that we verify the accuracy. And in this way, we can trace properly all the way down from the instruments that we use back to that primary standard. So here's an example of a hierarchy of standards for a thermocouple. Right? So the thermocouple was calibrated using a platinum resistance thermometer, right, which had an order of magnitude better accuracy than it. Okay? That platinum resistance thermometer was verified using another platinum resistance thermometer that again had a order of magnitude less uncertainty. And lastly, that the transfer standard platinum resistance thermometer was calibrated using a fixed thermodynamic point, which is physically defined and has no uncertainty at all. So very, very minimum uncertainty with the primary standard. So this allows us to understand what the level of uncertainty is for these different instruments. And it allows us to quantify the uncertainty for these different instruments. So in order for us to get, I guess, good comparisons between different experiments. So if I'm in Europe and I'm running an experiment and I want to compare it to a colleague who has an experiment in the United States, we often want to use what are called test standards and codes. So test standards and codes are developed by different technical societies and typically by a committee of experts. So some examples of these different societies that have different standards and codes include the ASME, the ASTM, ANSI, and ISO. Okay, so you can look up these different types of standards for different types of measurements, but these are the societies that regulate most mechanical engineering testing. All right, so in here I have a pretty simple example of a simple measurement system that has different um, purposes. So we have a caliper, a ruler, and a tape measure. All of these are used to measure length, right? Depending on your application, each of these might have a benefit to you, right? So a caliper has the smallest range, but it has the highest resolution, right? It also has the highest cost to use. The ruler has a moderate range, about a foot. It has decent resolution, around 20 thousandths of an inch. It has the cost of around $8, so it's the cheapest, and in a lot of cases it's totally acceptable for you to use. All right, and then the tape measure has the largest range, it has the worst resolution, and it has moderate cost. So depending on a situation of what you need, oftentimes in instrumentation you can use different instruments to take the same measurement, but one instrument might be optimal depending on what is the range of values that you need to measure and what's the required resolution that you have and your budget. So all of these things play a role in selection of appropriate instrumentation. So there's not always a best, I guess in the case of instrumentation, is a relative choice.